And it is my pleasure today to open the Skorokhod Readings. It is 9 Skorokhod Readings. The conference, which is aimed to give a possibility to young people to present the first results in probability theory, especially in the theory of random processes. Let me for a moment demonstrate my screen. And here is a picture of Anatoly Vladimirovich Skorokhod, who was the founder of our department and one of the prominent mathematicians of previous and current century in the field of theory of probability. Together with Joseph Ilyich Gichman, he developed the theory of stochastic differential equations. His name you can meet in any textbook devoted to stochastic processes. And it is interesting that Anatoly Vladimirovich always paid a lot of attention to work with young people. It was organized in his own way, namely, he always insists that you have to bring something value. He always asked, where is your result? What you want to say? In mathematical language, of course. And it was very efficient and very interesting to speak with him about mathematics. So in our department, we decided to keep this tradition to work with young people and to give them possibility to present the result, to discuss the new and first results in probability and theory of random processes. This was the reason why we created this conference. As I said, this is a 9th such conference. We hope that we will keep this tradition further. Today, as I said, it is my pleasure to open this conference, and I wish success to all participants of the conference. That's all what I wanted to say. And let me introduce the first speaker today. It is Igor Chulakov with the title Skorokhod Reflection Problem on Graph. Please, Igor.
Yes, thank you very much for the opportunity to give a talk. I am glad to present our work with Andrei Yurievich, Skorokhod reflection problem on a graph. First of all, some words about the classical ordinary Skorokhod problem that was introduced in 1961. It's actually a very comprehensible task. We have a function and we want to build a reflection in the usual sense of this function from axis x from x6. So why it is important? Because reflections always appear in a lot of fields such as QN theory, physics, chemistry, finance, and it can be easily seen how they appear, for example, in QN theory, because you can have some function that describes some Qs, and this function can be strictly can be only non-negative. So when our function tries to go below 0, we need to reflect here somehow. There is the following formulation, rigorous mathematical formulation of the Skorokhod reflection problem, that for a given trajectory W, we need to find two functions, x and L. X should be non-negative, and function L should be non-decreasing in such way that it can only increase when the x is 0. And it's a known fact that the Skorokhod reflection problem has, for continuous function, it always has a solution, and this solution is unique, and we even have the explicit formula for function L. For this function, it's actually is a running minimum of a function W. The philosophy of this problem is that we want to have some new function x that behaves itself exactly like function w, but only in the positive part of our graphics, and it cannot go below 0. On this picture, you can see at the same time both our original function w. By green, you can see its reflected function w. It can increase only when function w tries to go below 0 and tries to go even more below that level that it ever reached before. Yes, and by black, you can see exactly the Skorokhod reflection of function w, and it can be clearly seen that the graphics looks very similar for w and x. They, in the positive part of the graphic, x behave exactly like w, but with some shift, and it cannot go below 0. So our goal is to build the similar mapping like a classical Skorokhod reflection, but on a graph in the space Rm. In our work, by graph we mean exactly the star graph, the coordinate graph, not like in discrete mathematics. You can see graph inner 3 on your screen, and we want to do something similar. We have m functions, basic functions w, and we want to glue in some natural way their trajectories on the positive part of a graph. To do this, we start from another problem. We want to glue naturally on the coordinate graph trajectories of two m-dimensional functions, w and non-decreasing function r. W is before our original basic functions, and r will play the role of some compensators that are meant to push our trajectories of w up from 0 when w tries to go far below 0. To visualize what we are doing, not for the purpose to not draw multidimensional pictures, we actually can make pictures on the plane, just using different colors for different axes. For example, here the first axis I draw by blue. Here on this on left picture, it's our basic functions. On the right picture, it's our it's some trajectories which will play a role of our compensator, which will push us above away from 0 when our basic functions tries to go below 0. Yes, and there are of course a lot of what is exactly x? X represents the process on the graph. So how we should read this picture in this part on axis x, by the axis x, it's our time. So for a time period from 0 to 3, because we draw in blue, that means we use our first function w1. We live on the first coordinate of the graph, and at times when we switch to red color, and from 0 to 4, you can see here red line. It means that on the second red axis, our process is 0. And in some time, for example, here in time 4, we can switch the axis. Our process on first axis comes to 0, and we switch to second axis. And at this time, when we have switched, our first axis stay at 0, and only one axis at a time can become non-zero. That's what we want to do. Of course, there are a lot of different ways how we can glue together such trajectories with conditions that we leave always on a graph, that there are no coordinates bigger than 0 at one time. I want to say that it would be further convenient for us to cut trajectories of our compensators in such way that they would not increase simultaneously, that there are some queue. First increase one, then another, and so on. Why is it convenient for us? Because it would be very convenient for us to write a formula for our finishing process X, and it would be very convenient if we will have the same time for all compensator functions H. And you can see the problem if two functions H, red and blue, increase simultaneously. We will have the problem that at some point our compensators will push us away from the graph. Because on the graph, at least one of our coordinates is 0, and this thing will increase all our coordinates, and we go away from a graph. So this cutting of functions H is actually very convenient for us. And the question is what we can see in the limit of such processes X if we will cut them in some tricky way. Here, for example, I have glued together two functions. It's like something like cosinus and something like point cosinus, and I made the same rule for the following rule for cutting, that we have to turn on our compensating regime where our basic functions, basic it's without dots, when our basic functions go to some level, I have drawn this level by gray. When we touching this level and try to go below it, we should to switch to our compensating regime, because here we are on the first axis, on blue axis. This compensator should be, of course, blue, because if it would be red, it would push us away from the graph. And the question is, what will be if I will make this level which oblige us to switch to compensators more and more closer to 0. Actually, this is here in this picture was not, we have not there the W2, and here we have it. So here the level of switching is 1/2. When we go 1/2 with minus, we should to switch to our compensator. And here I introduce another rule. We should actually not just use our compensators randomly. They are exactly for what they meant to be. They should push us away, push our original trajectories away from 0. So I don't want that we use these compensators far below 0. So actually it has here level epsilon, some level epsilon, here I have level plus epsilon, and I just want for us not to be allowed to use our compensators below this level. So when we reach this level, we should again switch to our standard regime. Yes, and also only in points 0, we can switch also not only the regime compensating and not compensating, we also can switch our axis. And here we switch our basic regime of first axis to basic regime of the second axis. And the same rules are follows. Again, we need to use compensator in this level. Here we cannot use compensators, we go back. And I suppose that we have some cyclic rule that we, after two iterations on the each color, we should change the color at 0. Yes, and interesting question is what will happen if we will set the limit behavior or limit look of such processes that are drawn with this rule, if I actually will try to make this epsilon smaller and smaller. And I made some pictures of what it looks like when it goes smaller. And I suppose it can be see some tendency here. And I think it's actually already clear that it's actually similar that we had with the Skorokhod reflection. So on our graph, we can see almost only our basic trajectories, W1 and W2. Our compensators here almost cannot be seen. They are restricted for very, very small corridor. And our resulting process xt, it contained almost in the positive half of a graphic. It can go far below, and we see that in positive part of our graphic, trajectories of x actually is glued trajectories of our initial functions w1, w2. Here, yes, it's our initial cosinus and pointy cosinus from this picture. Yes, also except this, we will have some sticking in 0. And you actually can see that the stickings are quite long and longer than sticking in the original Skorokhod problem. And they are related to parts where our graphics basic function go below 0, and also they are associated with our compensators. If we change our compensators, make them grow faster and smaller, the length of this corridor can also shrink or enlarge itself. So actually, it's clear that I have we can make a lot of rules like this one that I introduced with switching, because I made actually a very clear rule when we should switch here, and in 0. After 2 iterations, we change the color. Another question is which will we have some limit, which rules we should make for this switching, and in which will we have a limit at least, and if we have limit, in which sense we have this limit, pointwise, maybe locally uniformly, and so on. And of course, it's clear if I give another rule for switching, the answer will be completely different. For example, imagine the rule when I don't have this part of my rule, when in 0 at some time I should change the color. Imagine that we always switch only from only in blue on the first axis, and only in this point reach this level, and so on. So in this case, even in the limit, we will have not any red part of our second trajectory W2. So clearly, the answer depends from the rule we give. Okay, and in our work, we introduce formal definition of such gluings. We call it we call such axis as a graph switching problem for functions w and h. As before, w are our basic functions, h are our compensators, and here we have some shifted time. We expect from them to not increase simultaneously. They actually behave like time, so they are not negative these times. They start from zero. They are non-decreasing, and we expect that they not increase simultaneously. We actually can separate our timeline R plus in intervals AK, BK, BK, AK plus 1. We can separate our time in these intervals, and at each interval only one of time functions. In total, we have n plus 1 time functions. Only one from this function can increase. Here, some strict rules for this function. So actually, time functions ti, they are really good. They actually increase. They are piece linear functions. They are rather constant, or they increase with angle 45. With angle 45, at one time. At one interval, only one from these time functions can increase, and we have not such strict rules for function TB. It actually can increase, for example, with jumps. Yes, and this rule exactly about what I said before. Our time functions cannot increase simultaneously. We have time we call a basic regime, where it can increase only functions Ti. Functions associated with basic regimes. And we have the unique compensator TB. It can increase only on the set of times B. We call it the compensating regime. Yes, and I want to note that from definition, it's not actually follows that for any functions WH exist at least one such gluing. And for some functions WH, there are more than one solution for the graph switching problem. As I mentioned before, we would have problem. We would had not any solution if our compensator functions h1, h2 increase simultaneously. It's not possible if we have a solution. So we investigated this definition and have proved some limit theorem. That when we have the sequence of basic functions, a sequence of compensators, and we have a sequence of graph switch solution for graph switching problem, our basic functions and compensators converge locally uniformly to sub-continuous function. We also have these technical conditions that can be described simply by words. What intuition this implies, this condition? It means that when our index n become larger and larger, it is prohibited for us to go far below zero. It means that we should switch to our compensators that should push us up from zero. And the second condition can be intuitively read like in our compensator regime, because of this bit, only in our compensator regime, our finishing problems for big N, they cannot go far above zero. Like in our pictures before, when we try to go up from zero in compensating regime, we obliged to switch to basic regime. Yes, and this following conditions, this should be interpreted like the follows. For huge N, asymptotically, time functions Ti increase almost everywhere. So our compensating regime Bn, where our compensating time Tb is allowed to increase, with n going to with n going to infinity, this set it shrinks in some sense. It becomes smaller and smaller, and asymptotically it has a Lebesgue measure 0. Yes, and of course we want that our compensators, at least in the sum, would be strictly increasing functions, because we want that our compensator would really act like compensators. We don't want to have for all I, hi like constants. That would be bad, really bad compensator. Yes, and what's next? If we have the following technical conditions, we can claim that there are such continuous functions, actually continuous functions xi, ti, tb, such that we can extract a subsequence nk such that our solutions to Skorokhod, sorry, not Skorokhod, graph switching problems converge locally uniformly to this function. So we have some convergence. And what's the question, what is this function xi? We actually not only want to know that there is some limit points, we want to know how exactly this limit point looks. And the answer to this question is here, that here and here. So actually time function, sorry, not time, function x, our limit function, is given by the formula, but this follows the next question: what is this functions ti and all? What is functions ti in this equation? Answer is the following: functions ti are the solution to this balance equation. Balance equation is the system 2. And we actually right now have something remarkable on our screen. Look exactly here. In this picture, big LWI, it means Skorokhod reflection problem of WI. And here we can see something interesting. We can function W, and it's a running minimum in sum. And we have already seen this today. It's exactly Skorokhod reflection of WI. But with some...
Igor, excuse me, you have just 2 minutes more, so please pay attention to this.
I'm sorry. Yes, and okay, so this theorem actually claims that our sequence of solutions xn is relatively compact, and the limit points of this given by the following system. But another difficult question is how much solutions have this system? Has it the unique solution? Has its solutions at all? And we have proven another theory about the uniqueness, that with some technical assumptions of our functions Li and Hi, we can claim actually that yes, this system, the balance equation, it has the solution and it has unique solution. And what actually this gives us, we can claim that our sequence of solutions xn, this xn, it's a relatively compact set, and this relatively compact set has the unique limit point, and it's equivalent as xn has a limit. Yes, and this limit is given exactly by these two formulas, 3 and 2. Yes, and very quickly, we used developed theory to prove even stochastic results that formulated almost like previous theorems, but in terms for stochastic process and everywhere except local uniform convergence, we have weak convergence, and we have generalization for the process. And for the process we have exactly the same formula. Yes, and we also has applied obtained result to build a Walsh-Brownian process. Yes, just by having some initial Brownian, multidimensional Brownian motions that starts from graph, we build it in such way that when it reaches 0, we should be necessary add some jumps, and we can write such process by the following way. We can easily, actually really easily check that all these functions that appear here, we can check easily for them all the conditions for our existence theorem, for our uniqueness theorem, and we actually claim that such Brownian motions with jump is really convergent somewhere. Moreover, we investigated where it is convergent, and it appeared that it converges to Walsh Brownian motion. Yes, sorry, I have not enough time. I can.
But we started a bit later, right? I think like 5 minutes later.
But we have a schedule. Okay, I think that we have to stop because we must have some questions. So just one or two questions, please. Okay, thank you very much for interesting talk. And now we have to go to the next presentation. The next speaker is Chang-Wei Guang with the talk Privacy Data Pricing Based on Stackable Game Approach. Please. I think that the speaker is here. So let's check. Oh. Okay, let's wait for a moment. I cannot see him right now. He was present, but now I cannot find him.
Maybe before he meets us again, let me make a few comments on Igor talk.
Okay, please.
So the aim of Igor talk was to glue dynamic on a graph, and in one-dimensional case, so dynamic assumes that it behaves like one Brownian motion on one in one ray, another Brownian motion in another way, and so on and so forth. And we introduced these compensating modes that pushes our system to different rays when you cross zero or when you touch zero. And under very general condition, it appears that Igor's limiting procedure has a limit. And this limit is almost continuous function of these W's and of compensators HI. And it allows us to prove a lot of functional limit theorems for perturbed random walks on graphs under minimal conditions, and conditions are just convergence of noises, convergence of compensators, and almost nothing. So Skorokhod reflection problem is continuous math. It helps a lot when we consider problems like heavy traffic limits and so on and so forth. And our approach helps us to consider complicated dynamics on graphs. Okay, so other next speaker.
I don't see him. Right now, I am asking Katerina. Can you just send him a letter?
Yes, I can. Give me a moment.
Please do it. Where is he?
Maybe if you have a moment, then I have a question related to the previous talk.
Okay, please. We have a lot of time now.
Thank you. So I wonder if it's possible to incorporate some delay at 0 into this model by maybe not making the switches instantaneous in the limit.
So there is no delay in Igor's talk. However, it's possible. It's next question. So originally, I started with Andrei Sarantsev when we considered one-dimensional dynamics, and we glue normal mode and compensating mode, and depending on certain condition on this compensating, we were able to obtain usual Skorokhod reflection, but also delayed processes like sticky Brownian motion and so on and so forth. Theoretically, it's possible to obtain here, but it requires additional work.
Yes,
Thank you very
actually, I
much.
think it's possible and not so difficult in terms of our conditions. Our jumps, our compensators are simultaneous. It's exactly this condition. If we will put it away from the theorem, I actually think it would not be proven very much different. We still could use Ascoli-Arcela theorem. I suppose actually maybe we will need a little bit some additional restrictions on functions TB. Maybe, for example, we can ask that they will be continuous, for example.
I see. Thank you.
Okay, Katerina, do you have something in answer from this?
Not yet.
Not yet. Then we have take a time until 16:30. Okay. Okay, let's try to continue. As I see, next speaker is present, and it is my pleasure to announce next speaker of our conference, Leila Jafarova, with the talk Sticky and Sticky Reflected Brownian Motion with sticky sets of Lebesgue measure 0. Please.
Thank you. Let me share my screen. So my topic is sticky and sticky reflected Brownian motions. My supervisor is Vitaly Konorovsky. And before I start showing my topic, I want to introduce you, remind you the definition of Brownian motion. It's such a stochastic process that defined on probability space and has these 4 properties. So it's 0 in 0 when t equal to 0. Bt minus Bs has normal distribution. B has independent increments, and B is continuous process. And here you can see the graph of Brownian motion. Yeah. Now I want to show my goal. For example, if we consider some Brownian motion that I denote by B, we know that it's Lebesgue measure when Lebesgue measure that B is equal to 0 is equal to 0. And my goal is to find such process X that looks like this B, but its Lebesgue measure in 0 is more than 0 with positive probability. And for that, I use time change method that was introduced by Ito and McQueen. They took some functional A that is equal to t plus 1 over mu and local time of B at 0. And then we denote a functional t that is inverse of A. And we use it as time. So B, instead of t, we have tt. And our x will look like this. This method also was used in Engelbert and Pesquier's paper, where they found that this system of equations, where x starts at x and mu is some given constant more than 0, they found that its solution, its weak solution, is sticky Brownian motion at 0. They also proved that the solution is unique and low, and there is no strong solution to this system. In my work, I also did something similar, but I didn't show that there is no strong solution. Another similar system was studied by Fadler, Grothaus, and Steil. This system where A set is countable, unbounded, and every compact subset of R intersects A infinitely many points. In this paper, they used Dirichlet form techniques in order to find the weak solution to this system. In my work, I have this system, and it's very similar to the system that Grothaus studied, but I used time change method that also was in Engelbert and Pesquier's paper. Also, I have these conditions. So L again is the notion of local time, and A is some countable set of measure 0 with one of the next properties. So it's either unbounded and every compact subset of R intersects A infinitely many points, as in Grothaus' paper, or the set is bounded, but we have this converging series for mu's from here. So the main theorem of my work is that there is unique and low solution to that system. What means solution to the system? It's some pair X and B for which this system satisfies. So if we have this, it means that X and B is solution to our system. And definition of uniqueness in low means that if we have 2 weak solutions, XB and X tilde B tilde, and low of X is equal to low of X tilde, it means that the solution is unique and low. Now I will need to prove this theorem, but before I want to have some, I want to show idea of my proof. If I denote B tilde as standard Brownian motion, and I define some functional R that is equal to this thing, which also can be rewritten like this if we have measure gamma is equal to this thing. We see that from construction of R, it's additive, continuous, and strictly increasing. So we can find its inverse that will be well defined and consider time changed process X that is equal to that B tilde with TT. Here, when we prove the existence of solution to that system, we first show that this satisfies, and the second one is this one. So it's the same as in the definition. Before I prove the existence of solution, I need to have these two equations. As we know that X is equal to B tilde with time change. And because the integral of B tilde being in A is equal to 0, we can write that B tilde is equal to this one. And using time change, we can rewrite it like this. Then we take the quadratic relation of B tilde. It's equal to T because B tilde is standard Brownian motion. And from the previous equation, we know that it's equal to this one, which also can be written like this because the red one is equal to 0. And because of the definition of R, how we defined it, we can rewrite it like this. We use some time change where we get RTS, which is equal to S. So we have this in the end. So I do this because I will use these two equations in my proof. Now we define another B0. B tilde we already had, but we take B0 as independent on B tilde Brownian motion on the same probability space. And we defined another process B that is equal to this expression. And it is continuous martingale from the construction. And its quadratic variation will be equal to T. And that's why by Levi's theorem, we see that B is Brownian motion. And also from the construction of B, we see that this equality holds. So in the end, we have that we had it before this part. And this part we get from the first equation that I had, this one. And this equality holds from the previous one. But this also can be rewritten like the next one. So it's the final step of our first part of the proof. Now we need to get this equation for local time, which I made here. I fix some C from A and see that this integral is the same as this one because of the time change. And this one, because of the definition of R, we can rewrite like this. Because the first element is equal to 0, we can write it like this. And this is equal to 1 over 2 mu c and local time because of Skorokhod theorem. So in the end, we have that this thing is equal to the first. And because of the shift properties of local time, we have the last one. So it completes our proof of existence of solution. And now we need to prove that the solution is unique in law. Before I start proving, I want to show the structure of my proof. Firstly, I need to prove that this functional t hat that is equal to this one goes to infinity almost surely when small t goes to infinity. And because this proof is complicated, there are two cases, case 1 and case 2, and the second case can be divided into 3 subcases, which I also will prove. And in the end, when we already know that t hat goes to infinity, we can take its inverse and prove the uniqueness in law of solution to the system. So first I have auxiliary lemma. As I already told, t hat goes to infinity almost surely. And preparation for this lemma, in preparation, I will show that I will denote some things and I will use it in the proof after. This equation comes from the definition of local time. And for simplicity, I denote this integral by m and rewrite it again. Then I use equation for local time from my original system of equations and just replace the local time by this. Also, I find that quadratic relation of this m is actually equal to t hat from here. So now I start to prove. And I prove by contradiction. For example, I tell that t hat doesn't go to infinity with positive probability. But then it means that that quadratic relation of m also doesn't go to infinity because they are just equal. And if it doesn't go to infinity, it means that m itself also doesn't go to infinity because it's martingale. Now I denote t hat c as this integral and have this because of the construction of t hats. And if t hat doesn't go to infinity, it means that the sum should go to infinity. And if the sum goes to infinity, I have two cases. First case is when there is such c from A, such that t hat c is going to infinity. And the second one, when for all of these c's from A, t hat don't go to infinity, but the sum goes. It means that the sum is very big, but the summands are not. So now I consider the first case and I want to get contradiction for that. I fix such c from A such that t hat of this c is equal to infinity with positive probability. And then again, taking the equation from definition of local time that I had before and writing instead of this integral t hat c, I get that right-hand side goes to infinity because m doesn't go, c is fixed and t goes. But if the right-hand side goes to infinity, it means that the left-hand side also goes. But it's contradiction immediately. That's why we can move to the second case now. In the second case, we see that we have this, and this is equal to that integral. It means that we can also tell this as a probability that for infinitely many s, x's from A has positive probability. And now we see that the case 2 also can be divided into 3 subcases. The first subcase is that A is bounded, and we have this property. And this one is divided into two subcases. X is bounded and X is unbounded. And the third subcase is that A is bounded with converging series, this one. It's from the condition of our system. Now I will see the first subcase when X is bounded, A is unbounded. We fix some omega from this event that X is bounded. And by the picture, we can also see that if X is bounded, it means that all the values that X can take are in some bounded place. And A is unbounded, it means that they can be from everywhere. So if I think that these blue points are the elements of A, we can immediately see that X takes only finite numbers, can be equal to only finite numbers of elements from A, which means that this sum has only finite numbers of non-zero elements. But if the sum of finite numbers of elements is going to infinity, it means that there is some c prime, such that t hat c prime goes to infinity. So one of them should go to infinity then. But this contradiction with our case 2. So this has contradiction. And we move to the second subcase when X is unbounded. So A is unbounded and X is unbounded. We fix some point from A, again write the equation and see that because it's fixed, it doesn't go to infinity, and this also doesn't go to infinity by our assumption. We see that the right-hand side is bounded and the left-hand side is unbounded. So it's contradiction also. So we move to the third subcase when A is bounded. We have again the same equation, but we also divide by mu c from both sides and get this. Now we take sums over all elements from A from both sides. Here we use triangle inequality, which means that we have the third one. And here we can just cross sum over c's because they are the same. We have in the end this inequality. And now we want to denote this sum as V, like this. And when we denote it like this, we see that quadratic relation of these is equal to this one by the theorem of quadratic relation of integrals. And this less or equal to this, obviously. This sum is converging by assumption. And the integral is just t hat. t hat is bounded when t goes to infinity by our assumption, this also, so it's finite. But because v is martingale and its quadratic relation is less than infinity, it means that v itself also bounded here. So we now understand that this sum is bounded and this goes to infinity. So it means that the whole expression goes to infinity, and that's why the right-hand side also should go. The sum is finite, so it means that x goes to infinity. But it cannot happen because before we had this probability and a is bounded. That's why it's also contradiction. So it means that we already proved the theorem, and t hat goes to infinity when t goes to infinity, and we can take its inverse, denoted by this, and we can do time change, taking some process b1 equal to this, and when we take its quadratic relation, we see that it's also equal to t. So again, by the Levi's theorem, we can understand that it's Brownian motion. And then doing these calculations, we can actually get that r hat is equal to t plus sum. And by the construction, we see that r hat is strictly increasing and continuous. So we can also take its inverse. It will be t hat, proper inverse. And it means that x can be written like this, because this one is exactly t. And because of the previous construction of b1, we see that it's b1 over t hat. It means that all the solutions to our systems actually can be written like functionals of Brownian motion, and it means that the solution is unique and low. So, and also I want to tell more about the other equations that I have in my work. I have also something with sticky reflected Brownian motions, and also Engelbert and Pesquer also had sticky reflected Brownian motion in their work. There was such system where x starts at x and mu is from 0 to infinity. And they also again proved existence and uniqueness in law of this solution. And also you can see the graph. Here the gray one is reflected Brownian motion. The red one is the graph of local time. And the blue one is sticky reflected Brownian motion. Also, there is some similar thing, sticky reflected Brownian motion on omega, that was studied by Grothaus and Voskal. These authors constructed diffusions on this set with boundary gamma, and they again used Dirichlet-form techniques in order to find the weak solution of the system, which also will be sticky reflected Brownian motion. And my systems are on the next slide. I again used here time change, not Dirichlet form as Grothaus. And I have two systems, this one and this one. This one is sticky reflected Brownian motion on the interval 0 to 1. And this one is sticky reflected Brownian motion on ball with radius 1. And it's also similar to the things that Engelbert and Pesquer did, but I used Tanaka's book for proving existence and uniqueness in law. And also in the uniqueness in law, Engelbert and Pesquer use Skorochod's theorem, and I again use Tanaka's theorem there. So it's the difference. Also, you can see references if you want. That's it. Thank you.
Okay, thank you very much. We have some time for questions. Maybe someone have questions or comments, please.
Do you have,
Okay, please.
do you have any idea if the series is divergent? And for example, you have stickiness at the point a point of certain sequence that converge to 0, for example, and 1 over mu c is divergent. So maybe you can describe such process.
Which series you mean?
You had two cases. One case when A is unbounded and another case where A is bounded. Oh,
Yes.
so assume that A is bounded. And maybe next slide.
Probably you mean the assumptions from here. I have assumptions.
Yes. So assume that A is a sequence that converges to 0 and such that this series is divergent. 1 over mu C is divergent. And you try to solve this system, or you approximate this problem by problems where A is just finite and try to investigate the limiting process. So what happens?
But if we have that A is bounded, but this theory does not converge, we cannot prove uniqueness in law.
Okay, so my question was: assume it is unbounded, and you approximate it by bounded, by finite sets. What may be a limit of processes with stickiness? No, so this is just future generalization. So maybe you have an idea.
I'm not sure. I need to think more probably about it.
I do not know whether I may give some comments or maybe answer your question, Andrei Anatolievich.
I think that you can do. Why not?
Okay, thank you so much. Yeah, it is interesting question. And I think that this sum actually it measures whether there could be a situation that the process just will hit to the accumulation point and then will stuck there. Therefore, for the existence, I think that probably even just using the direct approach, you can also like make time change, but like the time change until this blow up that the process hits to the point and stays there and doesn't leave, but here we have to probably using also like additional computations and so on. And the moment we didn't consider that question because we just wanted to understand okay, what happens when we have a possibility like to visit say every point or not to stay in a fixed point, whether we can apply the approach of Engelbert and Pesquer with the time change, and whether we can construct the process constructed by Grothaus, but using a different technique. But the existence should be possible also in that case.
And in the second case, so theoretically, A may be rational numbers. And you have uniqueness.
Yes, if it is a portion of, if it is rational numbers from some interval and these mu are taken
Yes, and the series is convergent.
And weaker. Yeah. Then you will have it's as we see that we will have uniqueness, and moreover, when we will make inverse the time change in another direction, that we will get a Brownian motion. That actually the behavior somehow is similar to the behavior of Brownian motion in some sense. You don't have any kind of stuckness and so on.
And also, I want to note that these properties, they are used only in proof of uniqueness in law. So actually, we don't need it in existence.
And also, it is used to be sure that the series that you make the time change is convergent.
And I have also one more question. Do you consider, so in which class do you have uniqueness? In the class of strong Markov processes or Markov processes?
We had the definition uniqueness in law here. So just by this definition. We had uniqueness in law in the sense of this definition.
Mm-hmm.
Okay, thanks. So you do not apply the strong Markov property.
No.
Okay. Some other questions?
Maybe I ask the question.
Okay, please continue.
Leila, could you also say, you mentioned it about when you talked about the sticky reflected case, that you use the Tanaka theorem. What actually do you mean? Maybe you can say what the difference is between the Tanaka theorem and, for instance, what is used in the Engelbert paper, where they use that.
Tanaka's theorem, Tanaka's book, I used it because in the existence of solution, I needed to, the solution of my system is a Brownian motion, but bounded on the set, on the interval from 0 to 1. And I used Tanaka's lemma in order to make my Brownian motion like this. So I used some process that is equal to Brownian motion plus the element that has quadratic relation equal to 0. And in Engelbert and Pesquet, they used absolute value for the process because it should be just more than 0. But mine is from 0 to 1.
Okay, you mean for the construction of the
Yes.
reflected process from the domain, right?
Yes.
Okay.
Okay, I also have the following question and proposition. You just say that maybe in case of divergent series 1 over mu c, you have no uniqueness in law, yeah? And in my book devoted to measure-valued process, I propose the notion of measure-valued solution to such equation. So it is, roughly speaking, the conditional distribution of the solution with respect to initial Brownian motion. For example, for Tanaka equation, we just get this solution. It is a set of measures which depends on the Bernoulli sequence of plus and minus, which we apply these signs to excursions of Brownian motion. And it can be proved that such solution is unique. And this is my proposition for you. Just look at this measure-valued solution in order to understand the structure of your process and its conditional distribution with respect to initial Brownian motion, and maybe even in case when you will have this divergent series, you can get the uniqueness of these conditional distribution. Okay, that's all, and thank you for your talk. Now we have just 2 minutes to the next talk. Let us wait a little bit.
And probably the next speaker may share his or her screen in order not.
Hope he will do that, but before I have an announcement related to the speaker who missed his talk. He connected with Katerina and said that has some urgent situation, very sorry and so on, and asked to make talk tomorrow. Maybe after all talks which are in schedule. So we will make additional announcement about his talk. Please pay attention to our announcement today after the conference. Hmm. Okay, the next speaker at our conference is Yudin Yaroslav with a talk on the convexity of interacting particle systems in the plane. Please.
Okay, thank you. Good evening. Let me first introduce myself. I am Yaroslav, of the Lyceum, which is in Odessa, Ukraine, and I'm grateful for this for the opportunity to present my research today. I'm thankful to my supervisor, Anatoly Dorogovtsov, for the guidance in this mathematical journey. Okay, so the topic of this presentation is the convexity of interacting particle system in the plane. And we're gonna start off by discussing general fundamental types of such particle systems, and fundamentally they can either be random, that is, there is some random environment or medium in which a set of particles with collision is moving, or there is a deterministic flow where particles are governed by some differential equation which is deterministic. Overall, we are going to dive deeply into the second. The second situation where the dynamical system is deterministic. Although some additional theories may be deduced about the first environment, and although the second deterministic flow may still be very complicated despite the absence of randomity. And so the main questions of our research is how do geometric properties of particle configuration change over time? So we're going to study the long-term behavior of such geometric properties. There can be many, actually. Not only the convexity is highlighted here, but also the area of the convex hull, the perimeter, but we are going to focus on this one specifically. More precisely, we are going to study the time average of the convexity indicator, which is denoted as 1 subconv. And so we're going to discuss two deterministic models. The first one is mathematical billiards, where there are n particles moving inside a square. Those particles do not interact with each other and reflect from the boundary, and so this dynamical system is governed by the standard billiards rule. Also, we're going to study another dynamical system, and there are again n particles which move in a plane according to a system of differential equations. Those are linear differential equations with some perturbation term. First, we are going to discuss mathematical billiards. Let's briefly discuss the rules again. When a point hits a boundary, it is reflected according to the law of reflection. That is, the angle of incident equals the angle of reflection. And we consider n such non-interacting points evolving according to the above mentioned dynamics. Here are some examples of the trajectories unit square. And different points are denoted by different colors. So we denote the set of strictly convex configurations as conv. This is a subset of the phase space, and let one subconv be its indicator function. Our main results describes the asymptotic proportion of time during which the billiard points form a convex polygon. Basically, this is the primary result. For each point P, we denote its direction as alpha, and we denote R as the dimension of a rationals of the linear span of alpha 1 through alpha 2n. And let L denotes the topological closure of the trajectory in the phase space. Then we can deduce that the theorem states that the time average of the indicator function equals the spatial probability of finding a system in a convex state. But in order to prove this result, we're going to rely on the generalization of Kronecker-Weil theorem. Why generalization, you may ask? Because usually the standard Kronecker-Weil theorem is about the is equates time average and space average of continuous function. However, the indicator function is discontinuous. Therefore, we shall generalize the Kronecker-Weil theorem to for the indicator functions as well. So basically, these parts, the first parts of these statements is practically the same of those of the standard Kronecker-Weil theorem, and we generalize it to open sets, subsets of this closure for which the measure or the Haar measure of the boundary set equals 0. Then the time average of these indicator functions equals basically just the measure of A. We're not going to dive like deeply into the proof. However, I'm going to present an idea, the idea of the proof. We are going to approximate this indicator function from below and from above by continuous function. So we're going to construct two sequences of continuous functions which approximate our original function from above and from below. For those functions, we're going to apply the standard Kronecker-Weil theorem because they're continuous, and then we're going to use the monotone convergence theorem to conclude that this time average indeed equals the measure of A. So yes, that's the idea. However, we have not yet discussed how do this dynamical system of billiards and the one which is discussed in the Kronecker-Weil theorem relate to each other. That is, in the Kronecker-Weil theorem, we discuss the linear flow on the torus. So we're going to construct an isomorphism. Basically, instead of when a point collides with a side of the unit square, instead of reflecting the point, we reflect the unit square itself. And then we are going to identify those 2 by 2 squares into a torus. That's the isomorphism. Concluding, this isomorphism allows us to equate the time averages of the corresponding dynamical systems and phase average of the corresponding dynamical systems. Moreover, this second equality, which comes from the generalized Kronecker-Weil theorem, which we have proven to be true. Hence, by the obvious sensitivity, we have that the time average of the indicator function of the convexity equals the probability of finding the system in a convex state. That's all for billiards, and now we're gonna continue with the second dynamical system. That is, there are endpoints which are governed by the following system of equations. So for the derivative, basically it's a linear term plus some perturbation. Note that the perturbation ought to be bounded and ought to have a bounded Jacobian in order for the further results to be true. Also, A is just some diagonal matrix with positive eigenvalues, and we denote this as the center of mass. There are many examples of such perturbations. For example, these Kuromoto type perturbations satisfy those requirements of being bounded with bounded Jacobian. The Kuromoto type perturbations are given by this formula, and they satisfy those requirements. Next, However, the results of the following theorems are gonna work regardless of specific example. In order to prove this, deduce any results, we're first gonna introduce rescaled variables, UI, and say UI, and like differentiate them to find out that the derivative of UI of the rescaled variables is absolutely integrable on the time interval. Therefore, use of I converges, and those limits exist. Now we're going to state the main result of this of our work. So as we have stated, those limits exist, and if the minimum of the eigenvalues is greater than 4 and z, then for almost every initial condition, the time average of the indicator of the convexity equal the indicator of the convexity of the limiting configuration of the rescaled variables. Basically, we state like the same thing which we have discussed about billiards, the same quantity, but now it equals it is fully controlled by the convexity of the limiting configuration. And that is what we're going to prove in this presentation. So as we have already proved, those rescaled variables, they converge. So this part is already evident from what we have shown beforehand. So this part is already proven. And in order to prove, to conclude anything further, we're going to relate the convexity of the evolving polygon to that of the limiting configuration. We can basically clearly this transformation is affine, since it's a composition of but it's affine, and convexity is invariant under affine transformations. Therefore, we can conclude that at any time t, the convexity of original polygon equals the convexity of this rescaled polygon. Also, let me give you some definitions of the degeneracy of polygons. So it's called strictly a degenerate if no three vertices are collinear. The set of strictly convex non-degenerate configurations is an open subset of N. Therefore, if the limiting configuration is non-degenerate, we can just find some time t0, starting from which the convexity of the rescaled variables matches also the limiting configuration. Hence, under the non-degeneracy condition, and this is really important, because for now this result doesn't apply to those initial conditions for which the limiting configuration is degenerate. And so for under this non-degeneracy condition, we have that the time average of the convexity indicator equals the limit the indicator of the convexity of the limiting configuration of the rescaled variables, as was stated previously. However, right now there's an enormous issue because this doesn't apply to degenerate configurations. Therefore, to somewhat avoid this problem, we're going to prove that the set of initial conditions which lead to degenerate limiting configuration has a Lebesgue measure 0. And that's going to be the most interesting part, really. So, in order to do that, we're going to start off by providing some definitions. First of all, phi sub t is the flow of the rescaled variables, and we define the limit map phi, which is dependent on the initial conditions of this flow. It exists, as we have shown earlier. Those k sub I are they exist. And those are the, let me remind you, those are the limits of the rescaled configuration. Also, we denote D, like this curly D, as the set of degenerate polygons. Note that this set is an algebraic set, an algebraic variety. Hence, it has measure 0. But our goal is to show that the set of initial conditions which lead to those degenerate configurations equals 0. Thus, we take the inverse of the limit map and prove that its measure is 0. Now, suppose for the sake of contradiction that it's not true. That's this measure is greater than 0. Then, by the regularity of the Lebesgue measure, there is a compact subset with again measure greater than 0. And we are going to derive a contradiction from there. So let us first prove some auxiliary theorems and lemmas. To control the measure of the inverse image, we analyze the Jacobian of the flow and prove that the determinant of the Jacobian of the flow is bounded from below by this exponential function, where this is some constant for nd times t. Okay, and we are going to use this theorem to deduce the following lemma, which is needed to bound the measure of set B in order to derive a contradiction. And so the measure of B is bounded from above by some e to raise to the power of basically some exponential function times the measure of the image of the initial set. And so this proof is quite straightforward. The flow is since the flow is a C1 diffeomorphism, and yes, since that we can conclude that this result holds. And we're going to use the change of variables here. Like, it's not really written down in full detail, so I cannot quite comment it completely, but overall, we use the smoothness of the flow. Next, there are two more lemmas. The first one states that this image is contained in thinking tubular neighborhood of the degenerate of the set of degenerate configurations. So basically, as we pass time to infinity, like if we consider this limiting configuration, this initial sets converges to this set D, and therefore the whole image in some tubular neighborhood. Also, we in this lemma we also note the specific value of this delta for which the image is located in the delta neighborhood. The other lemma is that for any compact set K, there exists a constant m sub k such that the measure of the intersection of the tubular neighborhood and K is less than or equal, is basically bounded by a linear function. Okay, but how are we going to utilize these three lemmas? We're gonna use them in order to constrain the initial measure. First of all, let's choose that set K, because we're gonna need some compact set which contains every single which contains the images for sufficiently large, the images of the initial set for sufficiently large T. And we are going to choose this set but by just noting that since the set converges, the image of the set converges uniformly to some degenerate configuration, because remember the assumption, we assumed that this set is the set of initial conditions leading to degenerate configurations. Therefore, starting from some sufficiently large T, all those initial conditions are going to be located within this closed epsilon neighborhood. Hence, we can just choose K to be this neighborhood, and yeah, we have chosen it now. So let's finish the proof. First of all, by lemma 5, we have the bound on the measure of the set of those initial, basically on the measure of B, the exponential bound. Next, we see that the image of B is contained entirely in this in the tubular neighborhood. We have shown this in the lemma 6. Hence, we also know the construction image is contained within K as well. Therefore, this image is in the intersection of both sets. Now, hence we conclude that the measure of the image is less than or equal to the measure of this intersection. Hence, applying lemma 7, which let me remind you is this is the linear bound on this on the tubular neighborhood. We conclude that there is some constant mk such that the image of set B is less than or equal to this coin. Now let us substitute this bound into the upper inequality, which is located here. And clearly conclude that the image, the measure of the initial set B is less than or equal to some constant times an exponential function. Recall, however, that one of the core assumptions was the fact that the eigenvalues of matrix A are large enough. Specifically, that mu is greater than 4 nd. Hence, this exponent is straight up negative. Therefore, if we take time to infinity, this measure must be less than any positive number, which contradicts our assumption of positivity. And that's basically all. We can now deduce a contradiction straight up from the facts, straight up from the original assumption of that this measure is greater than 0. Thus, negating our assumption, our failed assumption, the set of initial conditions leading to a degenerate limit configuration has measure 0. Therefore, let me remind you the original theorem, actually. Let me put it on the screen. For almost every initial condition, this time average of the convexity indicator equals the convexity of the limiting configuration of the rescaled system. And that's basically all for today. Thank you for your attention. I'm waiting for questions.
Thank you very much. Please, if someone have questions or comments. If not, let me comment that maybe a lot of people in today's audience know equations with interaction, and a lot of people spend time just thinking about the characteristics of the mass distribution evolving accordingly to the solution to equation with interaction. And the idea of this talk is to get another view, not to think about the covariance, for example, or the moments of the mass distribution, but to look at the geometric properties, at least of finite configuration. But for those of you who knows some statements about tube formula, or Lipton-Skilling curvatures, it is maybe understandable and easy to see that the work can be extended in this direction. And I hope Yaroslav will present next year the talk devoted to the evolution of such geometric characteristics of the some sets in the flow with interaction. By the way, it is related really to the Koromoto system, because the Koromoto system is the one of the simplest example where we have not just one point limit, but we have some partial synchronization effect, which means that we really can see some special configurations of the points. The same we can see in vortex dynamics. So I think that Yaroslav will continue these investigations. Okay, thank you again. And we still have a few minutes to the next talk. Let us wait.
By the way, Andrei, Yaroslav,
Mm-hmm.
have you thought about problems related to passive advection?
Related to what?
Passive advection. So imagine that you have a flow of fluid,
Mm-hmm.
and then you have particles which are advected by this flow. And these questions about convexity are very natural in this context.
Yes, yes, it is our plan to consider more complicated examples, and of course, as you mentioned, we are keeping in mind not only passive traces in the fluid, but also fluid with motion with interaction.
Exactly,
Yes,
yes, that's right. So one prediction people have is that the behavior will be very different depending on whether the flow is compressible or incompressible.
exactly, yeah.
Very nice. Well
Yeah,
done,
yeah.
Yaroslav. Very nice talk.
Thank you.
Mhm. Okay, now let us start our next talk. And speaker is Andrei Bobrov with the talk Kontorovich-Rubinstein distance on Gaussian spaces. Please.
Yes. So first of all, thank you for the opportunity. My today talk will be concerning 1 second. I just okay, everything looks fine. So my today's talk will be kind of a continuation of Rabov's works, where I will be exploring some properties of the one variational problem. So first of all, outline of my talk. So I will be step by step concerning some cases from very simple one-dimensional case to the kind of infinite dimensional case of a Banach space. The setup. We consider a separable Banach space and some centered Gaussian measure mu on the Borel sigma algebra on X. We also consider a Cameron-Martin space. That is the separable Hilbert space, which is densely and continuously embedded in X, such that the following holds. Basically, the following condition is just a familiar characteristic of a Gaussian measure using a notion of characteristic functions. In this expression, we have Lx is a functional, and here L is an element of the space, the corresponding element given by these representations here. Also, we will define a Kontorovich-Rubinstein distance on the space of Borel probability measures over X in the following manner. Here we have some two measures, mu0, mu1, and we consider every possible coupling. Basically, gamma of X times some measurable space will be mu1 of R, and I think most of us know what this joint measure basically is. Coupling is basically an alias for a joint measure. The interesting part of this variational problem is not its definition, basically, but the theorem, the property of this very distance h. Suppose our Hilbert space have an infinite dimensionality. Then this value is infinite almost everywhere. Yet we have this value actually being calculated to some finite value. So it is quite interesting even at this point.
So there is some spring in the theorem. You must wrote then norm xh is equal to infinity, yeah?
Yes, sorry.
Yes.
Yeah. At some point, we will be needing a way to assess our function using some weak conditions, and for this matter, we need to define a set of test functions. The set of the test function defined in a pretty intuitive manner. We define it as a set of cylindrical functions. Notice that this formulation is kind of taking an infinite dimensional function and taking it projection. But in the case of a Banach space, we cannot take projections since we don't have a Hilbert space structure. Yet we can use linear functionals to kind of mimic the behavior of projections. Here the function f is just a standard good function, which is smooth and bounded. We denote the set of cylindrical functions as fc infinity. On the space of cylindrical function, we define a stochastic derivative operator, which is defined as kind of mimicking a chain rule.
And mu is a Gaussian measure with Cameron-Martin space H, or mu is just arbitrary measure?
Mu is a Gaussian measure, which is associated with the Cameron-Martin space.
Thanks.
And we extend this operator, possibly to not bounded operator, on a whole L2 Also, we will need a stochastic integral operator I, which is just defined as adjacent adjoint operator of D. Basically, I is defined as this way. So the main theorem and the starting point of the stock is the following theorem by Ryabov. So suppose we have two probability measures such that they are absolutely continuous with respect to mu, which is Gaussian measure given at the beginning of the talk. Then, if we denote its density as G, we have the following relation. The Kantorovich-Rubinstein distance might be computed as infimum over all u, such that the stochastic integral of u is precisely the density. Yet again, this quantity here almost surely infinite. So the question which I was trying to solve is the following: do minimizing function exist? If it exists, is it unique? If it does not exist, in what sense it exists? In one-dimensional case, the setup is pretty natural. We have some centered Gaussian measure with Lebesgue density given by the well-known formula, and by using the characteristic function of the normal distribution and the fact that R star is basically R itself, in some sense, we can easily get the norm in this way. So camera matrix space H is a dense Hilbert subspace of X. The only possible Hilbert subspace is R, but we need to account that the space is altered by the measure mu. So using previous computation, basically the characteristic function, we can find the expression for the norm and the scalar product. Then we can find the precise form of the cylindrical function. In this case, cylindrical functions are just smooth functions with bounded derivatives. Also, stochastic derivative is easily found using Riesz representation theorem and given by this formula. And the adjoint operator might be found using integration by parts and the properties of Gaussian measure. Given all that, we can explicitly derive the differential equation and solve it. So here the multiplying and the integrating factor will be the density, and we in turn get the following equation, which is easily integrates, and the integrability constraints, since u should be the element of L square, by necessity force ux to be the only solution. And as a sanity check, we can check that ux is indeed a solution. By substituting the exact form of ux, we get this formula, and it is a well-known result in the theory of optimal transport that this is exactly equal to the Kantorovich-Rubinstein distance. In a multidimensional case, we have basically the same idea as to how we find the norm, the scalar product, the formula for stochastic derivative, but yeah, and how we can find the explicit formula for a stochastic integral. Basically the same idea, but we use multivariate integration by parts and so on. The interesting part is that now the equation is a continuity equation, which gives us a little bit a hint how we can kind of simplify the problem. By introducing a function j defined as follows, which represents the physical mass flux, we can change our objective function to be in the following form and satisfying this divergence constraint. But this problem is just a max flow, or also known as Bachmann problem. Here the intuition is the follows. So the function j of x is some vector field which shows how one measure is being transported into another measure. So ux gives us the direction and px gives us the amount of mass being transported. The crucial part is that given the flux j, we can always find the corresponding map flow and vice versa. However, in the case of RD, we lose uniqueness. Indeed, we can consider a following function. It is easy to verify that this function maps to 0 using, so the stochastic integral of u is 0, but at the same time, u is an L2 as it is just average distance of a Gaussian random variable from origin, which is indeed finite. So here we lose our uniqueness. Now I will talk a little bit about the existence, because here things become a little bit harder. I want to consider bounded sequences, but in L1, note that since we're minimizing this quantity, we should work in L1, but our constraints at the same time say that integral of u should be in L2. So it might be misleading, but we work in L1. So the idea is to embed L1 into the space of radon measures by basically the function j corresponds to j the mu. So basically j becomes a density of some function. This embedding is in isometry. But this approach allows us to take some bounded minimizing sequences, get corresponding sequences of measures, and using Banach-Alaoglu theorem, we can extract a weakly convergent subsequence. Since the subsequence weakly converges to some limiting measure mu star,
Excuse me, can you more precisely say how do you use Banach-Alaoglu theorem here? Because at least if you have the space of continuous, even bounded function on RD, I think that we have some measures which can be which can lose weight. Or how do you use Banach-Alaoglu theorem here?
Basically, the idea here was that the space is separable, so we can basically taking the bounded sequence, we can embed it. So the idea was that if my sequence is bounded, I can embed it in a good space, and in this space,
But
Banach-Alaoglu theorem work.
Let me ask you, this C0 is the space of functions which goes to 0 or are with compact support?
With compact support.
But it looks like it is not a Banach space.
No. It is a space of functions that goes to 0 at infinity.
Oh, I see. Okay, it is separate Banach space. Then we can apply Banach-Alaoglu theorem and get the weak limit. Okay, good. Thank you.
Thank you for the comment. But basically, since the limit is weak star limit, it natively enjoys the divergence constraints. Also, semi-continuity of integrals, or Fatou lemma, also known as Fatou lemma, guarantees that mu star is indeed the minimizing measure. So as a summary for the RD case, we lose uniqueness, but with lose uniqueness, we don't have a convergence to function, but we have a weak star converges to some radon measure. Then we move to infinite dimensional case of a Banach space. Now again, X some separable Banach space, and we minimize the total
By
variation.
the way,
Mhm.
sorry for
No, it's okay. Quick.
this slow reaction, but can you show us the previous slide? You
Yeah,
just
sure,
said
sure.
you said that this minimizer is a Radon measure. Can it happen that it is not absolutely continuous with respect to measure mu, and so how, in which sense it will help us to solve the transport problem?
That's a very good question because I don't know whether it is absolutely continuous or no. I want so it is like the next part of my research to investigate the properties of this measure.
Okay, thank you.
Yeah, thank you
Let's
for the
go.
question. Yeah. So now we have a general case of a separable Banach space, but here we even don't have this good. We don't have a way to use Banach-Aloglu theorem. This the way that I used it previously. Still, as was mentioned previously, we can have some measures which mass of which escapes to infinity, which kind of hints us to use not the boundedness but tightness. And the idea here is to use tightness. We still consider the space of Radon measures, but now it is measures of h-valued measures on X. Now I want my sequence to be not bounded, but just tight. Since our X...
Okay. What does it mean tight for h-valued measure?
Oh. Let me think, okay. Very good question. I think it should be that the norm of integral of the norm should be bounded by epsilon, I think. Yeah, very good question. It's very bad that I think I cannot answer to it right now, huh? Because... Wait, wait. Ooh.
I think that it means that for a large enough compact set in X, the measures of this compact set are concentrated on a large enough compact set in H.
Yeah, it should be this way.
We
It should be
use
somewhere this way.
h-valued Radon measures. So what does it mean h-valued? It means that values of measure
Yeah.
are Hilbert valued.
Yes,
So
yes.
what does it mean concentrated? Up to the norm of a remaining set.
Yeah, so up to some epsilon, these values they have to be in some compact set in H.
And so please I can write. So you mean that mu of X minus compact set norm is less than epsilon. Am I right, or what do you mean?
No, it's not less than epsilon. It doesn't belong to some compact set in H.
O does not belong to some. It is interesting. So it is totally new definition. So please, can you give us the definition of what does it mean? Because it is interesting.
No, but this is exactly what I said. Yes.
Since thus our marginals are supported on compact sets up to, but what does it mean that Hilbert valued measure is supported on compact sets up to arbitrary epsilon? Because you say it is Hilbert valued, yeah? I don't understand exactly what does it mean to be supported on the compact set for Hilbert valued measure. I understand what does it mean for usual real valued measure. We just said, okay, the remaining space has the measure which is less than epsilon. It's fine. But now your measure has Hilbert values. So what does it mean now?
I think you can just replace boundedness by compactness in the definition.
Boundedness by compactness. So
We still have a problem here.
What do you mean? Maybe you can write here also, not only me. Can we have a definition of what is tight for measure which is which has Hilbert values?
Okay, I think it should be actually as you've written previously. So for a regular tightness, we have x minus k less than epsilon. So here we need to just take, it's maybe, no, I think it should work this way, but actually it's very, very nice question, and I'm glad you asked it.
Okay, suppose that you use such definition, then you have to check Prokhorov theorem and Coulomb theorem with this definition for Hilbert valued measure. How we can do this with this definition?
Just directly try to check it. I mean,
yes, surely we have to try. At least it looks that every coordinates has such property. Yeah.
Yes.
But how we can collect together all coordinates to get the estimation? Yeah.
Yeah.
Well, I think that this is a point that we have to include in our proof.
Let us suppose right now that we have such. Okay, let's think. It is an interesting question. At least for people who study Banach spaces geometry. So it can be. I think
I used the result of De Acosta. That states that actually, if we have such condition for one the dimensional group projections, then we can combine it into like the tightness in the space of Hilbert valued measures.
Well, it will be interesting to look at it. Please send me the paper. Okay. Okay. For the moment, let us believe in it, because we have not enough time to discuss it. But it is interesting question, yeah, itself.
Yeah, very interesting. Thank you.
Okay. Let's go for it. Let's go for it.
Yeah. So if we suppose that this definition makes sense, we can use our compact set for mu0, mu1 to kind of trap mu_n. So again, this approach will work for like our spaces that we know how to work with. But the idea is that we can use the tightness of our mu0, mu1 to uniformly tight the intermediate measures. And this way we use Proctor's theorem. We extract in some weakly convergent subsequence. And now we're left only with checking if it satisfies the constraints. So since every function, if it is every cylindrical function and its gradient is also some bounded continuous function, we have that the following formulas hold true. Basically, the same computation as with case for RD. So this is our divergent constraint. It holds because mu n is sequence which satisfies divergent constraint in the same time, since mu star is a weak limit. This equality holds true, and therefore we have that our divergent constraint also holds true. So again, the constraint in a weak sense here, because divergence of measure is something very strange, to be honest. We have that the constraint is satisfied, and the minimality again follows from the photo lab. And so summary, in R we have some explicit ODE which is easily integratable, and integrability constraints force us to have a strict uniqueness. In RD we lose both uniqueness of solution and that it is function, it will become some measure. In infinite dimensions we even cannot use Banach's theorem, but we can at least try to apply some Prokhorov-like approach, Prokhorov-like theorem, and something like tightness, or maybe generalize the notion of tightness and extract the existence of h-valued random measures. And so the question, as was asked, is minimization measure absolutely continuous? I don't know. We will try to think about it. Maybe we will prove some result. The next question is, what is support of this mu star? And maybe there are some conditions on measure mu0 and mu1 that the minimizing measure is unique. So this is the next points that I will be considering. Thank you for your attention. If you have questions, please.
Okay, thank you very much for your talk. Maybe some questions or comments, please.
Okay, so I'd like to comment a little bit on this. In the formulation of the Beckman problem, this flow J, it defines like flow of maps that sends one measure into another measure. So it is, I think it is an interesting question, like how the optimality of J influences the optimality of the flow of maps.
Okay. Okay.
Yes, and also this idea with like not an optimal vector field, like an optimal measure valued field is interesting.
Yeah. Okay, thank you. And we have just 1 minute to next talk.
Thank you for the discussion.
Now we have to switch to next talk. The next speaker is Mikhailo Naumov with the talk Integrability of Composition of Functions. Please.
Okay. Hello, everyone. Thanks for the opportunity to present. Okay, so now I have to share my screen, right? With my slides. Do I have this? Okay, is it visible for everyone? No, it should be full screen.
Yeah, it's okay.
Okay, so yeah, hello, my name is Mikhailo Naumov. I work for Vola Software. I'm not professional mathematician, unfortunately, but I want to present the results that we obtained together with Professor Alexander Kukush, and we are thankful to Dr. Georgy Ryabov because all these results been discussed with him as well, and we got fruitful ideas. So first, well, we described the problem. We have some sections about Riemann integrability, some special cases for continuous functions, Lebesgue integrability, and we'll follow up. All right, so basically the setup is the following. We have two functions, function f from segment to segment, function g capital, which is our external function. F is our internal function, and H is their composition. And we want to know when the composition is integrable. We'll first discuss integrability by Riemann, then by Lebesgue. So there's a classic fact that if F is integrable by Riemann and G is continuous, then their composition is integrable by Riemann. It's a known fact. So some literature references. However, this naively using it is fragile because there is example of two Riemann integrable functions, but their composition is not integrable. We will discuss this example in a minute. Main tool that we're going to use for this, I'm not touching anything. I'm not showing my video. It says
It's okay. It's okay now.
Did you see my previous slides?
Yes.
Okay. Okay. Thank you. So our main result for Riemann integrability is Lebesgue criterion, and it's well known criterion is that if function is bounded on a segment, so it's integrable by Riemann, if and only if the measure of its discontinuity set is 0. So this gives us due to there is obvious inclusion that discontinuity points of composition can be only a discontinuity point of f of inner function and pre-image of discontinuity point of external function. So the first part is not really interesting because in all our cases it's always going to be measure 0. So basically what's interesting is the second part. We're gonna look through examples. Okay, so motivating counterexample is also classical results. If R is a Riemann function, which is if we have rational point, the value is 1 over denominator in lowest term and 0 for irrational points. So such function by itself, it's continuous in all irrational points. So all discontinuous are only rational points. So they measure 0. Therefore, it's okay. We said f is R. So f is integrable, and we take G capital as an indicator of half interval. So its discontinuity point is only 0.0. So also measure 0 and also Riemann integrable. However, their composition is a Dirichlet function, which is discontinuous everywhere, and therefore it's not integrable. So this is a classic result of two Riemann integrable functions. Their composition is not integrable. So our goal is to find mild condition guaranteeing that H is integrable. Okay, so we could obtain some nice criteria that I didn't see before. So first of all, we have sufficient condition, which is quite obvious. If we just demand that the second part, the difficult part, already given that it's measure 0, then composition is integrable. Okay, so from the previous slides, we have this statement, and comparing their measures, we see first summand is 0 because f is integrable, and second summand, even we took external measure, but as its measure is 0, external measure is also 0, so they're all zeros. So this is a very simple theorem, but it gives sufficient condition for integrability. But this condition is not necessary. So easiest counterexample is that we have a function that is defined on like that, and it's like that. So it is. We can see that that function f, function and function g capital would be just indicator of 0. Then their composition is an indicator of entire interval from 0 to 1/2, which is integrable, but pre-image of discontinuity points of G has big measure. So this shows that this condition is not necessary. So we are looking forward to fill the gap. Okay, first we got a criterion when we fix external function. So we found that if we fix capital G function and we want for all possible inner functions their composition to be integrable, it turns out it happens if and only if the G is continuous. From right to left, it's the sufficiency is a classical fact that we already shown, but the necessity is not. At least I didn't know that. I couldn't find such fact. It's even if G is discontinued in one point, we can construct a such function f breaking the composition. And the idea is the following. We take the so-called fat Cantor set with positive measure, and we using it with some transforms. We define continuous and therefore integrable function f that is constant on this fat Cantor set, and it makes small tens on complementary intervals, oscillating j across its jump. So if you build it accurately, we can prove that the discontinuity points include k. So its measure is positive, and therefore composition is not integrable. It's missing the integrable on AB. All right. The criterion about internal function is more difficult, and here we need well, first we define what is n inverse property. We call that a function has n inverse property if it maps null sets to null sets. Like that. Corresponding n property is the other way around. If just function f is applied, and my minus one, it's different property. Okay, this is the useful thing that we need to get from discontinuity points of G to their pre-image. This is studied in some article where this term, I believe, was introduced. And we also we will use this property in Lebesgue section because it guarantees facts needed for that section. Okay, so we have a sufficient condition that if we fix a function g, no, we don't fix it here. Just some function, and f is having this n inverse property, then their composition is integrable by Riemann. But again, this is not necessary. Simple example is a constant function, which doesn't have n inverse property, but their composition is also constant, so also integrable. So that's not a necessary condition. However, we can transform it into criterion by adding additional requirement. If we also require that f is nowhere locally constant, so meaning that there's no interval on which it's constant, then it becomes a criterion. So for any external function, their composition is integrable if and only if f has an inverse property. This is a deep result, and it completes the previous criterion. Sufficiency we discussed on a previous slide, which is easy part. Necessity is more difficult. Basically, we need to build counterexample. If f doesn't have an inverse property, we need to construct a capital G function in a way that it breaks the composition. And the idea of the construction is the following. So we assume that f lacks an inverse property. Then we prove that there is a Borel set with zero measure, but positive pre-image measure. And then we define measure mu, which is measure of pre-image. And as we know that mu of n is positive, positive, so mu is not absolutely continuous with regards to lambda, Lebesgue measure. So we split mu in a Lebesgue decomposition into two parts, which second part is I don't remember how it's in English, orthogonal to Lebesgue measure, and we know
singular to lambda.
Yeah, thank you. Yes, singular to lambda, and so it's concentrated on the it's concentrated on n, but we can also prove that it's can be concentrated on a compact of measure 0. Then we know that for any Borel set M, its indicator is Riemann integrable, and basically what we need to find M such that measure of a border of preimage is positive. That's difficult part, and it splits into cases regarding preimage of K, and there are three cases to consider when it's Sig boundary, if it has an atom, and if it's non-atomic. In each of these three cases, we build corresponding M and proving the theorem. Actually, this from the proof, it which I didn't show, but from the proof, it's seen that this nowhere locally constant can be relaxed to say that n inverse is just to demand that n inverse is on a complement of constancy set. All right, that's the biggest result achieved. Now let's talk briefly about continuous and absolutely continuous functions. So we want to show that even if we have monotone continuous function which doesn't have n inverse property, still it can be shown that composition is not integrable. So we take a classical staircase function theta, and we slightly smooth it with adding x and halving it, and we consider capital G as indicator of counter set. So classical counter set with measure 0. So function G is integrable, but their composition of f and G is not, because f sends counter set C into fat counter set K, and so it converts from 0 from null set to non-null set, so violating an inverse property. And we show that by criterion H has non-zero discontinuity set, so it's non-integrable. So it shows that by itself, just being monotone and continuous is still not enough to maintain integrability. We'll introduce a technique, inverse Lipschitz technique. Basically, we defined that inverse Lipschitz technique condition is that difference of functions is bounded from bottom with some constant. And under this condition, we claim that upper measure of any subset is bounded by inverse constant and the measure of the image of the set. So intuitively, this happens shrinks segments, and then it applies to all sets. That basically gonna be the proof. We even show the proof. It's interesting by itself, and it's not too big. So let's fix the subset B, and let's consider some cover of the image of FFP with half intervals. So going back to pre-images, we get the following. And now we apply inverse Lipschitz condition. So we will get this inequality. And as we already bound X and Y in a half interval, so we go to the half interval bounds. So this helps us to get the measure of entire pre-image and bound it with the original bounds. So then we just add them up, and finally we can go to infinitum by all covers and get the desired property. We will going to use this property in this section and also in the section of Lebesgue integrable function. Okay, another result obtained in this section is that if f is absolutely continuous function with derivative, non-zero derivative almost everywhere, then for every function g, their composition is integrable. Basically, we show that we are using previous results about n negative condition by splitting AB in a pieces where f is locally inverse Lipschitz. We can apply that and get proof that the measure of pre-image is 0. Okay, so there are some examples. For example, that G for every integrable G of x squared and G of square root of x is always Riemann integrable. All right, that's it about Riemann integrability and Lebesgue integrability. We proved a few facts. Also, we assume that for functions that have inverse Lipschitz condition, then f is SS measurable. Where S is a set of Lebesgue measurable, is a set of Lebesgue measurable sets. Because it might be confusing at first, because you can ask, if it doesn't it mean f Lebesgue measurable doesn't mean that, but no, this definition just means that pre-image of any Borel set is from S. We're having stricter statement. We can prove that pre-image of every Lebesgue measurable is also Lebesgue measurable. Okay, so we this lemma that I just showed, it's converted to similar to Lebesgue integral. An example is like for x plus arctan x, as it satisfies the condition of the theorem, we can deduce that g of x plus arctan x is always Lebesgue measurable. Okay, and considering changing of variables. Similarly, we can deduce by changing variables that if such function is Lebesgue measurable, then such function is also Lebesgue measurable. So this is, and similarly, it's kind of inverse to that. Here we go from x to square, here we go from x to square root. And satisfy all the conditions, and we got the following results. And okay, so our main results are, we have general sufficient condition as described. We have a result for fixed external function. So it has to be continuous in order to be universal. Internal function has to have an inverse property, assuming additionally that it's nowhere constant. Interesting result about absolutely continuous function with non-zero derivative. And for Lebesgue measure, inverse Lipschitz is our main result. I think that's it. So I fit my schedule, ready for questions.
Okay, thank you very much for interesting talk. Maybe someone have questions or comments, please.
Yes, I have a question. So, Mitchell, you told us that unfortunately you are not a mathematician, but you are working in software development area. So, what is your interest to take part in such kind of researches? Why I spend time for such activities instead of, I don't know, doing cloud technology certifications or some kind of that?
Thank you for the question. I graduated from Kyiv National University about 20 years ago, and unfortunately, I went to be a programmer instead of mathematician. But mathematics was always my passion, and I do mathematics for my own hobby interests. I read many books, and I try to be in touch with some professors and participate in math circles. So this is
Okay,
math is my life.
thank you very much, but I think that we have to discuss mathematics firstly. Because if you like mathematics, we have to do mathematics. And I think that we have to prefer here mathematical questions. If somebody have mathematical questions, please.
Yeah, I have a question. It's Igor Fomenko. Mike, you just mentioned about several variables, possible generalization of that function superposition. But I'm more interested, in what is kind of how you can see relation actually with probabilistic concepts. What I mean that questions which you discuss and count examples and so on, it's closely related to when we try to define conditional expectation, right? When we select the different barrier files. Have you thought about any kind of probabilistic interpretation of your results?
I didn't investigate it in that matter, but when I was working on the proofs, some of the approaches, they were very similar to what we use in probability theory. So it's not like we do anything in probabilistic terms, but many approaches are similar. But from the other hand, many things from measure theory is very interconnected with probability. So,
I was just thinking about that interesting kind of combination of Lipschitz condition and then absolute continuity. And I thought that maybe we can somehow understand it in kind of probabilistically. It's just obviously I understand it's general question, but yeah. Maybe of I don't know even that area kind of variations of functions or whatever it's called in real analysis. No.
Okay, I have questions which are related to your question and maybe explain the answers. So the
Okay.
first one related to one-dimensional case. You mentioned the level sets, the images of the null sets under the one-dimensional mappings. It is closely related to the properties of semi-martingales when we study local times, existence and properties of local times for semi-martingales, and the sets where they are increasing. So I think that if you will look in this direction, you will get the examples of trajectories of random process with bad and with good properties, which can be described in your terms. This is a first comment. Second comment is about multidimensional case. Yes, the previous question was absolutely right, and it seems to me too that it is related to deep questions from probability theory. And it looks, I already mentioned this to Alexander Georgievich, that if we want to study locality property of differential operators on the multidimensional case, namely, if we have differential operator and apply it to two functions which coincide on some sets, when the results will coincide on the same set. And it occurs that we can characterize the sets in multidimensional case using Lebesgue's theorem about points of density. Lebesgue's theorem says that every point of density has one density 1 of the measurable set. But the speed of convergence can be very different. And it is related to locality property of differential operators, which can be described as some, as we had in previous talk of Bobrov, which can be considered as stochastic integrals, extended stochastic integral in Gaussian space. So I think that the talk is very interesting for probabilists, and I hope it will be expanded to multidimensional case. Unfortunately, we have no time. We even overrun the schedule. So thank you again. And the next speaker is Fei Kao with the talk "Fractal Opinions Among Interaction Agents." Please.
Professor Doros, could I just add I mean, first of all, thanks. It's actually very deep analysis of what I tried to say. I just want to mention two things. First of all, with level sets, there is famous, but not a lot of people know, but practitioners about level sets work of Banach. And second, your deep question about Lebesgue density points. Professor Kukush, I sent to him some my results in neural networks where exactly I used that concept of Lebesgue density points in combination with L2 shift subspaces. So thanks a lot. I think it was very deep what you said, and thanks a lot.
Can you send to me this paper too?
Yeah. I'll send.
Thank you.
It was even before I met the first time Professor Partenko in East Lansing.
Okay. Now we have to switch to next talk. So Let me introduce again our speaker, Fei Kao, with the fractional opinions among interacting agents. Please.
Hello, everyone. Okay, can you guys see my screen?
Yes, it's visible
Okay.
now.
Yeah, so I'm just going to show my recent joint work with Robert Codes, who is currently assistant professor in University of Verona in Chile, and I'm going to talk about interacting particle system modeling opinion dynamics. So the setup is we are going to first describe the model, and it's in the framework of interacting particle systems, and I'm going to study the large population limit, the so-called mean field limit. After we pass into the limit as the number of agents goes to infinity, we are going to recover a Boltzmann type PD at the mean field level, and we're going to study the large time behavior of the mean field equations, and when they discuss the stationary profile of opinions when t goes to infinity. Okay, so the model is like this. So imagine you have like n agents, where each agent is characterized by his or her opinion, and the opinion lies in the bounded interval from -1 to 1. You can imagine that the xi of t denotes the opinion of agent I and time t. And we're going to call this, you can imagine that xi of t denotes the political standpoint of agent I and time t. And you can imagine in the context of US politics, you can imagine agents with holding a value of holding an opinion of -1 will be like considered as extreme left, and agents with opinion +1 will be considered as extreme right, such as Donald Trump, okay, and his MAGA supporters. Okay, the dynamics goes as follows, and at the random times, we're going to pick two distinct agents I and J. Okay, imagine that agent I as a listener and agent J as a persuader, and the persuader agent J tries to influence the opinion of the listener agent I. We're going to pick the pair of Aij independently and uniformly at random. Of course, the selection is independent from the past selection as well. We're going to update the opinion of the listener agent I according to these rules. Okay, how is either going to move to +1 by a portion of mu plus, or it moves to -1 by a portion of mu minus, and with the corresponding probability. So you can imagine the larger the opinion of agent J, then for the agent I have a higher probability to go to +1. So the lower the opinion of agent J, I have the higher the probability for agent I to go to -1. So basically, this model exhibits conformity in language of social science. Okay, so if you imagine I'm a listener, I talk to a more right guy, I'm more likely to become right. Okay, if I'm talking to a Democrat, I'm more likely to become Democrat. The mu minus and mu plus are just measuring how fast I'm moving to the extreme opinions +1 or -1. Okay, so this is the setup, and we ask what happens when you play the game and you send in the number of population to infinity, and you play the game infinity many rounds. Okay, you're sending n and t goes to infinity. So let me record the existing results and the connection to existing model. So first of all, if you initialize the opinion of all the other agents, initially either take either value -1 or +1, and the parameters mu minus and the mu plus are exactly 1. So the Price model, this is actually corresponding to a voter model. Okay, you can either vote for +1, you can either vote for Republican or Democrats. Okay, this is a special case when you have the setup of initial values and the mu plus and the mu minus. Okay, and for obvious symmetry, we're going to always assume that mu minus is less than or equal to mu plus. Okay, because of the model symmetry. So the existing results tells you that if mu minus, basically if mu minus is different from mu plus, then you always have consensus. Okay. So for instance, if mu minus is less than mu plus, and you initialize the opinions for all the agents randomly. Okay, you initialize every agent's opinion initially is going to take a uniform random error from -1 to 1. Then you as t goes to infinity, and for each fixed n, all the agents' opinion is either go to reach a consensus at the right extreme or left extreme. Also, under large population limit, n goes to infinity, the event that you converge to all consensus at +1 is exponential to it's converging to 1. Basically, the event a-1 happens before event a1 happens is 0. So our goal is to it's a little bit sorry. Our goal is to analyze the model using a mean field framework. So we have the stochastic agent system, and we pass to the n goes to infinity limit first for fixed t, and after we derive the mean field equation, we pass in t goes to infinity, and we are going to study the long-time behavior of the mean field equation, where we recover the equilibrium. So based on this description, the only non-trivial case for the model is when mu minus is mu plus is exactly equal. So let me show you an agent-based simulation of this case. So I'm plotting the equilibrium distribution when mu minus equal mu plus equal mu, and for 5 million agents. So this is the equilibrium profile. So initially, when you study increased mu, it looks like a Gaussian, but when mu increase, you can see the equilibrium is increasingly fragmented, and when passing mu equals 0.5, is getting completely crap. Okay, so we'll see that after mu equals 0.5, you're going to entering a phase transition where the equilibrium is a uniform supported on fractal contour type side. Okay, so this is just the equilibrium. It's just a simulation. Okay, so let's talk about the mean field limit. Sorry. So at the mean field level, you can describe each agent's opinion by a stochastic differential equation. Sorry. Oh, sorry. It's a little bit. So basically, at the mean field level, we can describe the evolution of each agent by a stochastic differential equation. And when you're passing n goes to infinity, you're going to get a mean field SDE of this form. And basically, you're going to for the ZT represents as n goes to infinity the evolution of a typical agent's opinion, and it can either move into a fraction of mu plus to 1. Or a fraction of mu minus to -1, depending on a sign of the random Bernoulli coins. And if you we can prove the so-called propagation of chaos. Basically, we can quantify the distance between the law of the whole vector and the tensorized law of the mean field equation under the Wasserstein distance. And this can be bounded by a law of large number results. Okay, so you can see that if you simulate the agent-based model compared with the limiting mean field as the arrow decrease, the W1 arrow, the expected arrow decrease when n increase. So this is a kind of law of large number type of results. And the law, you can describe the mean field SDE by its associated comodular forward equations. So you can write down the so-called Boltzmann type PDE for the evolution of the typical agent's opinion in the mean field setting. So this is a Boltzmann type equation. It has a gain term and the loss term, and the MT is just the mean opinion of the average of the opinion rho t. So actually, you can compute from this Boltzmann type PDE, you can compute MT explicitly. So instead of the non-linear PDE, this is actually a linear PDE, but which is time inhomogeneous. So the second moment can be can be computed explicitly as well. So, but it's not useful for our purpose. So we mentioned some kind of results for the at the mean field level. We studied the large time behavior of the mean field PD. So as I mentioned to you, in the case of mu minus is different from mu plus, the result is kind of trivial. You are going to converge to a consensus at either +1 or -1. Okay, in the case of mu minus equal to mu plus, you are going to reach a consensus at +1. All the agents become the right extreme. So basically, you can show that the average opinion converges to 1, and the variance of the distribution converges to 0. So if you have a random variable whose law at mean 1 and the variance conversion to 0, you know that this implies that the rho t converges to a Dirac mass at 1, and you can turn this moments behavior into a quantitative bump in Weierstrass 1 or Weierstrass 2. Okay. Okay, so for the case of mu plus equal to mu minus, we can still establish the convergence to equilibrium, and basically our tools are you can either establish the convergence large time convergence to equilibrium either under a Weierstrass distance, also called Toscani distance, which is a Fourier type distance. Okay, this is in terms of the Toscani the Fourier based distance of order s between two probability laws on R with finite s moment is defined as follows, where the f hat and the g hat are corresponding to the Fourier transform and the f and g. S greater than equal to 1 is just the index, and we can show that if you have two solutions to the same mean field PDE and with a common first moment. By the way, when the mu minus equal mu plus, you actually the mean field PDE preserve the mean MT. Okay, so MT equals M0 in this case. You can show that a contraction type result in this case, and of course this contraction result immediately implies the convergence to equilibrium at the exponential rate. Okay, the proof is just you pass in the equation the mean field PDE to Fourier transform, and you do some like a ground wall type estimates. Okay, and that's the case when you're working with the PDE, and the results in Toscani distance or Fourier based distance can be there's a nice interpolation between the ds distance and the W1 distance. So basically, a control of ds distance gives you a control of W1. Okay, and actually, if you're working directly with the SD, you can refine the rate of convergence in terms of 8 to. If you're working directly on the mean field SD using a coupling approach, you can actually prove Weierstrass contraction with a better rate. Okay, and the proof is again we couple the two solutions to the same mean field to the solution. We couple two solutions to the same mean field SD starting from possibly different initial data, and we use the synchronous coupling, meaning that we pick exactly the same noise. And if you denote the HT of the expected value of the distance between two solutions of the same mean field SD starting from different initial data, you can get ground wall type estimates. Okay, that's the way you do it. Okay, finally we discuss so far we showed that when n goes to infinity, the agent-based model converges to a mean field SD, or which can be described in terms of the mean field PD, and we studied the large time behavior t goes to infinity for the mean field PD, and we showed that when mu minus is different from mu plus, you always converge to the Dirac mass, either centered at +1 or -1. And for the case of equal mu, we can still show convergence. But the next question is like, how does the equilibrium look like when mu plus equal to mu minus? Okay, we are going to assume that mu plus equal to mu minus, and in this case you can characterize the equilibrium in two different ways. The first way is the probabilistic characterization. So you can characterize the equilibrium the equilibrium distribution in terms of, if you talk about the random variable characterization, then you're going to characterize the Z infinity is going to equal in distribution the convex combination of a copy of itself and a random variable. So those Bn is a Radmacher random variable which takes probability 1/2 to be 1 and probability 1/2 to be -1. Okay, we're working with the M0, the initial value, the initial opinion to be 0. Okay, so this is a random variable characterization of the equilibrium, and of course you can iterate this fixed point equation to get the Z infinity in terms of the infinite series. So this series is a famous name. They are called Radmacher series or like Bernoulli convolution. So it's a convex, a kind of convex combination of infinitely many, countably many Radmacher random signs. Okay, and you can also characterize in terms of the Fourier transform. If you pass into the Fourier transform, you can write down the Fourier transform of the equilibrium law in terms of the infinite product of this cosine. So far, we showed that the so-called object equilibrium exists, and we somehow described the equilibrium, the way of characterizing it, either through a random variable or through an integral representation. We are going to show that the nature of this infinity changes vastly when mu passes the critical value 1/2. So first, the first result is that if mu plus equal mu minus equal 1/2, and the initial average opinion is 0, then actually to converge to the uniform distribution from -1 to 1 is a unique equilibrium distribution of the mean field PD. And you can verify that if you insert the Fourier transform of the uniform distribution, it satisfies the fixed point equation. And it also has a very heuristic geometric intuition. So basically, if you take a uniform random variable from -1 to 1, and you multiply by 1/2 because mu equal 1/2, and you get this distribution, and you shift to the left or to the right by a symmetric Radmacher random code, you recover to the same distribution. So this shows that the uniform distribution satisfies the random variable characterization of the equilibrium. And why you should expect the fractal structure to emerge when mu equals 1/2? So remember that Z infinity is the fixed point of this map. Z infinity equal 1 minus mu Z infinity plus mu times this independent symmetric Radmacher random code. So if mu is greater than 1/2, so if you take a random variable Z which has full support on -1 to 1, you multiply it by 1 minus mu, but then because mu is greater than 1/2, so 1 minus mu is strictly less than 1/2, so you're going to create a hole. And then you shift. So each iteration is going to create a hole, but you want to get a fixed point. So that's exactly the process you undergo when you construct contour set. Okay, if you take a contour set from 0 to 1 to 1, you from 0 to 1, and you cut the middle, keep cutting the middle, you're going to get the contour set. Okay, that's exactly the process. So you can show that if mu is between 1/2 to 1 and the initial average opinion is 0, then the equilibrium random variable is going to be a uniform random variable supported on a contour-like set, and you can construct the contour-like set exactly like the procedure of you constructing the usual contour set, and you can determine the Hausdorff dimension of this. It's actually not a fat contour set because it's actually how the big measure 0. Okay. So this implies the equilibrium distribution of the mean field PD is a singular. And that's the usual proof you can go through that's the proof process as usual when you prove that the cut in the middle process converges to a contour set. That's as usual. And yes, so there are some simulations showing that for mu equals 1/2, you should expect the contour set, because we cannot plot the seed in the PDF anymore. We're going to plot the CDF, and especially when mu equals 2/3, you have the beautiful staircase. So it's just a counter staircase function 0 to 1 stretched to -1 to 1. Okay, you have the beautiful staircase. The left side is the agent-based simulation. We plot empirical CDF, and the right is we plot the CDF for the mean field equation. Okay, so we have some partial results for mu less than 1/2. For instance, for this particular mu is 1 minus 1 over square root of 2. We can show that for instance the equilibrium distribution is like a trapezoid type equilibrium. It looks like this. You can think of the volcano, and then you can show that when mu is less than 1/2, and again we centralize the initial average opinion to be at 0. Then you can show that the scaled random variable, the equilibrium random variable z infinity, if you divide by its standard deviation sigma, is as mu goes to 0, it actually converges to a normal distribution. So these are some proof, and in the end, I'm going to show some simulations when mu is less than 1/2. So this is simulation for mu equals quarter. It's more like a Gaussian. The smaller mu, the more like it's going to resemble a bear-shaped curve. And so this is the trapezoid equilibrium we talk about. And lastly, when you increase mu, it's kind of increasingly getting more fractals. So just as a remark, so deciding whether the equilibrium distribution is absolutely continuous or with respect to Lebesgue or singular for mu equals 1/2, that's a famous open problem in fractal geometry. People have shown that for almost every mu less than 1/2, you should expect the absolute continuous equilibrium. But a decade ago, others construct a set of specific mu's that are called inverse Pearson numbers in algebraic number theory, at which the equilibrium is actually singular. So the mu is, if you think of the mu as a reciprocal of Golden ratio, so that's a number of Pearson numbers. And so far, this is the only known examples people can construct people can show that for symmetric Bernoulli convolutions, you have singular equilibrium. No other known examples are known. Okay. So the paper is published at some Journal of Applied Dynamic Systems, and we also extend the Priest model to asymmetric, to an anti-conformal case where you're interacting with Polar, with Democrat, make you more like a Republican, or interacting with a Republican, making you more Democrat. So this is our recent preprint. This is our recent print, which talks about a sibling of the model. Okay. I thank you for your attention. Please let me know you have questions or.
Okay, thank you very much. Maybe someone have questions or comments, please. Actually, I have one question. Can you please again show the equation for the stationary point?
You mean the mean field PDE or?
Yes. No.
Yeah, you mean this? You mean this?
No. Where you just write maybe this one. This one, yeah. Maybe this one. Okay. So my question is the following. Why don't to think about the following procedure to get the Z infinity? Let us just consider the family of random variables xi(n), which are ID, and have this B distribution. Excuse me. And has this distribution B. Then let us try to consider stationary solution of the recurrent equation, like xn plus 1 is 1 minus mu xn.
Yeah, that's exactly.
Plus, then you will get the series the series with the such coefficients, and this will be power series. Am I right?
Yeah, you're going to get the expression like this.
Yes.
This is called the infinite.
Yes, exactly. Then we have a statement that the law of this series must be pure law, just absolutely continuous, singular, or discrete in any case.
No,
And
the fractal geometry literature tells you you have a dichotomy. You either are absolutely continuous or singular.
yeah,
So
exactly,
there are no
exactly.
you cannot allow mixture of the two.
Yeah, exactly. So you use this approach, yeah?
Can you repeat that?
As far as I understand, you use this approach and use the statement from fractal geometry, because I think that we have a description when it is absolutely continuous, and when it is singular, we have those series of numbers which you mentioned. It is
The inverse
already
Piso
written.
number. The inverse Piso
Yes,
number.
yeah, exactly. So you use it.
No. I didn't discuss that. That's that. This work is trying to bridge opinion dynamics to the fractal geometry. We didn't study fractal geometry at all. So if you look at the paper, we introduced the agent-based model. We passed to goes to infinity. We studied the large time behavior of the PDE purely based on like stochastic analysis PDE technique. There's no fractal geometry. So that's the astonishing part, that we somehow covered the well-known object in fractal geometry, which has been studied a decade ago since Earth. Also, I want to emphasize that in a related preprint, as I mentioned at the end, so you can find out. Okay, so we study a sibling of this model, as I mentioned. So the model we study is just a slight difference of this rule. So for this model, if you interact with the Republican, you become more like a Republican. Interacting with Democrat, you become more Democrat. But if you change, okay, let's say if you change this plus to minus and this minus to plus, is in social science language is anti-conformity. So imagine you talk with someone, you can either become, okay, I like you, I become more like you, or okay, I hate you, I want to go away. Okay, so by talking with a Republican, you can either go become more Republican, or okay, I'm going to like Democrats more. Okay, so in that model, we generalize the so-called Bernoulli convolution. We discussed the fractal, which has not been appeared in the literature, and we don't know how to study the absolute continuity, etc. in that case. So that's in terms of the robustness, that preprint is more, it contains more interesting results than this one.
Okay, thank you very much.
And if you have three parties, is it possible to get similar recurrent equations?
Can you repeat that?
If you have three parties.
Okay, so it seems like you have like a left extreme. Okay, let's typical like the French, like European, like French, like German. They have like extreme left, extreme right, and the middle. Maybe some like Macron in the French president currently is like kind of middle. But you have to design. For instance, let's say some people is between minus 1 to 0. They talk to like the issue is that. If you design a three-party, the 0 is kind of awkward because the 0 is like is singular. I mean, you cannot carry. Okay. It's some like you have like a middle to left is from 0 minus 1 to 0, and from middle right 0 to 1, and you have whole singularity of let's say a positive fraction of people holding like a 0 opinion. You have to design a good model in order to study. I would say the concept is interesting, but I'm not sure if you can design interesting model for that. But it's conceptually it's interesting.
Yeah,
maybe you can cut something like a -1 to minus. I would guess if you really want to cut, you can cut 0 to 1 to minus 1 to 1 to minus 1 to, let's say, minus 2 over 3, then minus 2 over 3 to sorry, minus 1 to minus 1/3, minus 1/3 to plus 1/3, and plus 1/3 to. So in that case, the middle will be like more, instead of a singular 0, you can extend the middle party to minus 1/3 to 1/3. You can control the size. That's my suggestion.
But what if we have like not a segment, but like a triangle? So maybe that was the idea. If we have like 3 distinct vertices, and each agent can be between 3 vertices.
Okay, that's actually, but you know, in 2 dimensions, we consider the high dimensional extension of this. It's okay if you do if you just do a tensorized version of this model, for sure, if for certain parameter, it's going to cover 2-dimensional contour set, which is the contour dot. But I would like to. So you imagine the case of considering a triangle. That might be interesting, but I don't know how to design a model for that. In the end, you want to cover some other fascinating fractals, which is non-contour type, for instance, Shelby-Ski triangle, etc. You name it, the beautiful fractals. But I haven't. I tried, but I couldn't design a good model for let's say you have 3 index in a triangle. I have to think about it. Thank you for the suggestion.
I have a simple question. You mentioned that you used somewhere in your talk, I've never thought about it, like for partial differential equation or maybe SD, you used Fourier transform, and then
that's a very
and then it looks like in frequency domain you use Granol-Bellman technique. So I just want to understand interpretation. Is it kind of that growth of amplitude for big Fourier harmonics, it will be small, or what is it? I just
okay. So if you're not familiar with the Koenig theory, like the study of so these techniques are first developed by a group of Italian people like Toscani and his students Lorenzo Paransky, and they designed a model to study the Koenig the traditional physical Boltzmann type equation. They studied the various. They show that these two many canonical type, especially Boltzmann type or Fokker-Planck type equation, they take a much simpler form under Fourier transform, and then they design this Fourier-based distance, and which you can show. Cariano and Toscani had a very nice. I think I cite this article at the end. So this is a very good seminar work. I highly encourage you to take a look at the design.
No, I understand it, but it's kind of, for me, unusual. I always would use Granol-Bellman technique just for state variables, but it looks like they introduce some clever metrics, and you actually at first apply Fourier transform, and then you get your lemma Granol-Bellman's inequality, right? Or
yes, that's the root.
Okay, I just want to confirm, because it's something what I've never thought, that such duality could be useful.
That's why I highly recommend you check this. This is a very classical way to learn.
Okay.
Let me know if you have any other questions.
Okay, thank you very much. Other questions, please? If not, thank you again for interesting talk, and let us thank all the speakers from today. Let me recall you that one talk from today will be removed to the last place in tomorrow. Please pay attention to the announcement which we will send today to everybody, and hope to see you tomorrow. For today, that's all. Thank you for your attention. Bye.
Thank you.
Bye.
Bye.
Goodbye.
Thank you. Goodbye.